A modern freight locomotive can weigh over 200 tons and pull a train stretching over a mile long. Yet all that immense force is transferred to the rails through contact patches smaller than a credit card. How is it possible that steel wheels on steel rails don't just spin uselessly under such extreme pressure? Today, we're diving deep into the fascinating physics and brilliant engineering that makes steel-on-steel traction one of the most efficient systems ever developed. The fundamental physics, understanding friction and normal force to understand why locomotive wheels grip so effectively, we need to start with the basic physics of friction. The force of friction between two surfaces is governed by a simple but powerful equation, F equals mu times N, where F is the frictional force, mu is the coefficient of friction, and N is the normal force pressing the surfaces together. In the case of a locomotive, the normal force is simply the weight of the locomotive pressing down on the rails. This is where the first brilliant insight of locomotive design becomes clear. Engineers intentionally make locomotives extremely heavy. A typical diesel-electric freight locomotive weighs between 180 and 220 tons, and this massive weight is not a drawback, it's a carefully calculated advantage. The coefficient of friction between clean, dry steel surfaces is surprisingly low, typically around 0.25 to 0.4. This means that under ideal conditions, a locomotive can generate a tractive effort of roughly 25 to 40% of its weight. For a 202 locomotive, this translates to 40 to 80 tons of pulling, force enough to move thousands of tons of freight cars. But here's where it gets interesting. Unlike a car, where excessive weight reduces efficiency, a locomotive's weight is its primary tool for generating traction. Every pound of locomotive weight directly increases the normal force, which in turn increases the maximum frictional force available. This is why you'll never see a lightweight locomotive, though. Physics simply wouldn't work. Weight distribution, the strategic placement of mass. Not all of a locomotive's weight contributes equally to traction. Only the weight resting on the powered driving wheels creates useful traction. This is why locomotive engineers pay careful attention to weight distribution, ensuring that as much weight as possible rests on the driving axles rather than on unpowered trailing trucks. Modern six-axle freight locomotives typically have all six axles powered, meaning the entire locomotive weight contributes to traction. The weight is distributed across these axles through a sophisticated suspension system that keeps each wheel in contact with the rail, even over uneven track. This distribution typically places 30 to 35 tons on each axle, creating enormous normal forces at each wheel-rail interface. The suspension system itself is a marvel of engineering. It must be soft enough to allow wheels to follow track irregularities, maintaining constant contact, yet stiff enough to prevent excessive weight transfer during acceleration and braking. Primary suspension springs sit directly on each axle, while secondary suspension systems support the locomotive body, creating a two-stage isolation system that optimizes both ride quality and traction. The contact patch, where physics meets engineering. The actual contact area between a locomotive wheel and the rail is astonishingly small, typically about the size of a dime or quarter for each wheel. This small contact area creates contact pressures exceeding 200,000 pounds per square inch. At these extreme pressures, the steel actually deforms slightly, both elastically and plastically, creating a complex interaction zone. The wheel profile is not flat but slightly conical, typically with a taper of about 1 in 20. This conical shape serves multiple purposes. First, it provides a self-centering effect that helps guide the wheel set along the rail. Second, it creates a variable contact patch that adjusts based on lateral forces. When the wheel set shifts slightly to one side, the effective rolling radius changes, creating a steering moment that guides it back toward center. The rail head is not flat. Either it has a curved crown that matches the wheel profile. This crown surface ensures that contact occurs at a specific, predictable location, maximizing the effective friction coefficient and minimizing wear. The combination of conical wheels and crowned rails creates what engineers call a conformal contact, where the surfaces naturally fit together to distribute loads effectively. Creep theory, the surprising truth about wheel slip. Here's something that surprises most people. Locomotive wheels actually do slip slightly during normal operation. And this small amount of slip is not only normal, but necessary for generating maximum traction. This phenomenon is called creep, and understanding it is crucial to understanding locomotive traction. When a locomotive wheel rotates under load, the contact patch experiences enormous tangential forces. These forces cause the wheel to deform elastically, creating a situation where the front edge of the contact patch is moving slightly slower than the wheel S. Rotational speed would suggest, while the rear edge is catching up. This creates a small velocity difference, typically 0.5 to 2%, between the wheel surface speed and the actual forward speed of the locomotive. This creep is essential because it allows the full frictional force to develop across the entire contact patch. Without creep, only static friction would be available, and the transition to motion would be abrupt and unstable. With controlled creep, the friction force builds progressively, creating smooth, controllable traction. The relationship between creep and tractive effort follows a characteristic curve. At very low creep levels, tractive effort increases linearly. As creep increases, the tractive effort reaches a maximum at around 1 to 2% creep. Beyond this optimal point, creep continues to increase, but tractive effort actually begins to decrease, eventually leading to gross wheel slip where the wheel spins freely with minimal forward motion. Modern locomotives use sophisticated control systems to maintain operation at the peak of this creep curve, maximizing traction without crossing into unstable slip conditions. This is one of the key advantages of AC traction motors over older DC systems. They can modulate individual wheel torques hundreds of times per second to maintain optimal creep levels. Sand, the original traction enhancement system, despite all the sophisticated engineering. Sometimes the coefficient of friction between steel wheels and steel rails simply isn't enough. This is where one of the oldest and simplest traction aids comes into play: sand. Locomotives carry several hundred pounds of dry sand in hoppers mounted above the driving wheels. When additional traction is needed, such as when starting a heavy train, climbing a steep grade, or operating on wet or contaminated rails, the engineer activates the sanding system, which delivers a controlled stream of sand directly in front of the driving wheels. The sand increases the coefficient of friction in several ways. First, it provides additional abrasive particles that increase mechanical interlocking between the wheel and rail surfaces. Second, it can help break through thin films of water, oil, or other contaminants that reduce the steel-to-steel contact. Third, under high pressure, the sand particles can actually embed slightly into both the wheel and rail surfaces, creating temporary mechanical keys that enhance grip. Modern sanding systems are pneumatically operated and carefully controlled. The sand must be dry. Moisture causes it to clump and clog the delivery pipes. The flow rate must be optimized. Too little sand provides insufficient benefit, while too much can actually reduce traction by creating a layer that acts like ball bearings between the wheel and rail. The delivery angle and position are also critical, ensuring the sand reaches the contact patch at precisely the right moment. Interestingly, sand is consumed relatively slowly during normal operations. A locomotive might use only a few pounds per mile, even when sanding continuously, meaning a full sand load can last for hundreds of miles of difficult operation. However, replenishing sand is a routine part of locomotive servicing, as it remains one of the most reliable traction aids available. Electronic wheel slip detection and control, while sand has been used for over 150 years. Modern locomotives incorporate sophisticated electronic systems that prevent wheel slip before it becomes problematic. These wheel slip detection and control systems represent some of the most advanced aspects of locomotive technology. Each driving axle is equipped with a speed sensor that continuously monitors its rotational velocity. A central computer compares the speeds of all axles in real time, looking for discrepancies that indicate incipient wheel slip. When one axle begins to rotate faster than the others, indicating it's losing traction, the system can respond in milliseconds. The response depends on the type of traction motor system. In DC systems, the field current to the slipping motor is temporarily reduced, decreasing the torque and allowing the wheel to regain traction. In AC systems, the inverter that controls each motor can precisely modulate the current and frequency, providing even finer control over wheel torque. These systems don't simply cut power when slip is detected. That would create a jerky, inefficient response. Instead, they implement sophisticated control algorithms that smoothly modulate power to keep each wheel operating at its optimal slip point. The system continuously probes for the maximum available adhesion, backing off when slip increases and advancing when conditions allow. Some advanced systems also incorporate accelerometers that measure the locomotive's actual ground speed independently of wheel rotation. This provides an absolute reference that helps distinguish between wheel slip and legitimate acceleration, improving the system's response accuracy. The benefits of electronic wheel slip control are substantial. Locomotives can develop higher average tractive effort because they can safely operate closer to the adhesion limit without risking gross slip. Wheel and rail wear are reduced because sustained slipping is prevented. Fuel efficiency improves because power isn't wasted spinning wheels. And train handling is smoother, reducing stress on couplers and cargo. Traction motor technology. AC versus DC systems, the type of traction motor used fundamentally affects how a locomotive manages wheel slip and generates tractive effort. For decades, DC traction motors were standard, but modern locomotives increasingly use AC motors, which offer significant advantages for adhesion control. DC traction motors are series wound machines, where the field and armature windings are connected in series. This creates a motor characteristic where torque naturally decreases as speed increases, ideal for railroad applications. However, DC motors have limitations in how quickly their output can be modulated, and they typically connect motors in series parallel arrangements that limit individual wheel control. AC traction motors, specifically three-phase induction motors, are controlled by individual inverters that can adjust both frequency and voltage hundreds of times per second. This provides unprecedented control over the torque at each wheel. If one wheel begins to slip, its inverter can instantly reduce power to that specific motor without affecting the others. This individual wheel control delivers several benefits. First, it maximizes total locomotive tractive effort, because each wheel can operate at its individual adhesion limit rather than being constrained by the wheel with the poorest adhesion. Second, it reduces wheel and rail wear, because sustained slip is virtually eliminated. Third, it allows locomotives to operate effectively under widely varying rail conditions, without requiring constant engineer intervention. AC motors also provide better adhesion at low speeds, which is precisely when locomotives need maximum tractive effort when starting heavy trains. The low-speed torque characteristics of AC motors, combined with precise inverter control, allow modern AC locomotives to develop their full-rated tractive effort from a standstill, something DC locomotives struggle to achieve. Dynamic braking, preventing wheel lockup while we've focused primarily on traction during acceleration. The same physics apply during braking, except now we reconcerned with preventing wheels from locking up and sliding rather than spinning. This is where dynamic braking becomes crucial. Dynamic braking uses the traction motors as generators, converting the train's kinetic energy into electrical energy that S dissipated as heat in large resistor grids for DC systems, or fed back to the power system for AC systems with regenerative capability. This provides smooth, controllable braking force without relying solely on mechanical friction brakes. The advantage for adhesion is significant. Dynamic braking can be precisely modulated to keep each wheel at its optimal slip point during braking, just as wheel slip control does during acceleration. If a wheel begins to lock up and slide, the dynamic brake effort on that wheel is automatically reduced. This maintains directional stability and maximizes total braking force while minimizing wheel and rail damage. Modern locomotives can develop tremendous dynamic braking forces, often 50,000 to 70,000 pounds or more, which is sufficient to control heavy trains on steep descending grades. The system works effectively across a wide speed range, though its effectiveness decreases at very low speeds where generator action becomes insufficient. Rail surface conditions, the ultimate challenge. Even with all these sophisticated systems, rail surface conditions remain the limiting factor in locomotive adhesion. The coefficient of friction between clean, dry steel surfaces might be 0.35 to 0.40, but this can drop dramatically under adverse conditions. Wet rails reduce the coefficient of friction to around 0.202 to 0.25, cutting available adhesion by nearly half. The thin water film acts as a lubricant, preventing full steel-to-steel contact. Rain-soaked rails present challenges, but the first rain after a dry period is often worse because it mobilizes accumulated dust and creates a slippery paste. Ice and snow create even more severe conditions, with friction coefficients potentially dropping below 0.10. Under these conditions, a locomotive might generate less than 10% of its weight in tractive effort, barely enough to move itself, much less pull a train. This is why winter operations in cold climates require special procedures, frequent sanding, and sometimes even reduced train weights. One of the most insidious conditions is leaf contamination. In autumn, fallen leaves on the rails get crushed by passing trains into a thin, incredibly slippery layer that's been compared to black ice on roads. This leaf film can reduce friction coefficients to 0.05 or even lower. European railways, which run through heavily forested areas, have developed specialized rail cleaning trains and chemical treatments to address this seasonal challenge. Oil, grease, and diesel fuel spills also creates severe adhesion problems. These contaminants are particularly difficult because they're not easily displaced by sanding, and they can spread along the rails as trains pass over them. Maintenance procedures emphasize preventing these spills and quickly cleaning them when they occur. Adhesion modifiers and rail conditioning to address problematic rail conditions. The rail industry has developed various adhesion modifiers chemical treatments applied to either the wheel or rail surface to improve traction. These fall into two main categories: positive friction modifiers and friction management systems. Positive friction modifiers are applied to the rail top surface to increase the coefficient of friction under wet or contaminated conditions. These materials typically contain solid particles suspended in a carrier fluid. When applied, the particles remain on the rail surface, increasing mechanical interlocking between wheel and rail. Some systems can increase the friction coefficient from 0.15 under wet conditions back up to 0.30 or higher. These modifiers are carefully formulated to provide benefits without creating buildup that could cause problems. They must work across a wide temperature range, resist being washed away by rain, and not interfere with track circuits used for signaling. Application systems can be mounted on locomotives or specialized rail treatment vehicles. Friction management is slightly different. It involves applying controlled amounts of lubricant to specific parts of the rail to reduce wear while maintaining adequate top-of-rail friction. The gauge face of rails on curves receives lubricant to reduce the lateral forces, and wear from wheel flanges rubbing against it, but the top surface where traction occurs must maintain high friction. Advanced friction management systems use sophisticated applicators that can selectively treat different parts of the rail profile, lubricating wear-prone areas while preserving or even enhancing friction on the tread surface. This represents a holistic approach to rail management that optimizes both wear and traction simultaneously. Wheel profile management. The profile of locomotive wheels changes gradually through wear, and this evolution significantly affects traction performance. New wheels have a precisely machined conical profile, but as they accumulate miles, wear patterns develop that can either enhance or degrade adhesion characteristics. Hollow wear, where the central portion of the wheel tread wears faster than the edges, is particularly problematic. This creates a wheel profile that doesn't match the rail crown properly, reducing the effective contact area and changing the stress distribution. Adhesion can suffer, and the risk of rail surface defects increases. Locomotive maintenance programs include regular wheel truing, where wheels are machined on specialized wheel lathes to restore their proper profile. The frequency of truing depends on annual mileage, the types of rail encountered, and the aggressiveness of braking practices. High-mileage locomotives might require wheel truing every few months, while others might go a year or more between services. Modern wheel profile designs are the result of extensive computer modeling and real-world testing. Engineers optimize the profile shape to balance multiple competing objectives, maximizing contact area for adhesion, minimizing rolling resistance, reducing wear rates, maintaining steering stability, and preventing harmful stress concentrations. Different profiles may be specified for different services: drag freight, intermodal, passenger, or switching operations. Each have different priorities. Multiple driving axles, distributing the load. Another key reason locomotives achieve such impressive traction is that they distribute the driving force across multiple axles. A typical 6-axle road locomotive has all 6 axles powered, spreading the tractive effort across 6 contact patches rather than concentrating it on just 1 or 2. This distribution provides several advantages. First, it reduces the peak stress at any individual wheel-rail interface, staying further below the limit where gross slip occurs. Second, it provides redundancy. If 1 or 2 wheels encounter poor adhesion, the remaining wheels can compensate. Third, it allows the locomotive to navigate uneven track while maintaining traction, as the suspension system keeps all wheels in contact even when the track alignment varies. The mechanical arrangement that allows all axles to share loads while accommodating track irregularities is remarkably sophisticated. Each axle is independently suspended and can move vertically several inches. The axles are typically grouped into trucks bogies of 3 axles each, with the trucks themselves able to pivot relative to the locomotive frame to navigate curves. Traction motors apply torque to each axle through sophisticated gearing. In most designs, the motor hangs from the truck frame with one side of its gearbox attached to the axle. This nose-suspended arrangement allows the axle to move vertically while keeping the motor properly positioned. More advanced designs use fully suspended motors with flexible couplings to the axles, reducing unsprung weight and improving ride quality. The electrical control system coordinates all these motors, ensuring they work together efficiently. In DC systems, motors were often wired in series parallel groups, which meant some motors shared current paths. AC systems with individual inverters for each motor provide independent control, allowing each wheel to develop its maximum possible tractive effort, regardless of what the others are doing. Starting heavy trains, the ultimate adhesion challenge. Perhaps the most demanding test of locomotive adhesion comes when starting a heavy train from a standstill, especially on a grade. This scenario combines the highest required tractive effort with the most challenging adhesion conditions. Low speed with minimal creep development, a fully loaded freight train might weigh 15,000 tons or more. Simply overcoming the starting resistance, the force needed to get the train moving can require 30,000 to 50,000 pounds of force per locomotive. On a grade, gravitational forces add substantially to this requirement. A 1% grade adds 20 pounds per ton to the resistance, meaning our 15,000-ton train faces an additional 300,000 pounds of gravitational force, pulling it backward. Engineers use several techniques to start such trains. First, they take advantage of coupler slack. Freight car couplers have several inches of play, and in a long train, this slack accumulates to 50 feet or more of total slack. By releasing the air brakes gradually while maintaining slack, the engineer can start the train one car at a time, gradually taking up slack from front to back. This allows the locomotives to accelerate small groups of cars sequentially, rather than fighting the inertia of the entire train simultaneously. Second, aggressive use of sand helps maximize available adhesion during this critical moment. The sanding system runs continuously, ensuring every driven wheel has the best possible traction. Some locomotives can deliver sand to wheels during both forward and reverse motion, providing bidirectional capability. Third, modern wheel slip systems are calibrated to allow slightly higher creep levels during starting than during normal running. This accepts a small amount of wheel slip as necessary to develop maximum starting tractive effort, while still preventing gross slip that would waste energy and cause damage. Finally, distributed power placing additional locomotives in the middle or rear of the train dramatically improves starting performance on grades. By pushing while the head-end locomotives pull, the train experiences more balanced forces, reducing coupler stresses and allowing smoother acceleration. The distributed locomotives are controlled remotely via radio, maintaining synchronized operation with the lead units. The future, advanced adhesion technologies, the quest for better adhesion, continues with several emerging technologies showing promise. Electromagnetic systems that use magnetic fields to increase the normal force at the wheel-rail interface are being researched, though they face challenges with power consumption and weight. Active suspension systems that can rapidly adjust wheel loading to optimize adhesion in real time are in development. Perhaps most promising are predictive systems that use weather data, track condition databases, and machine learning algorithms to anticipate adhesion conditions before they're encountered. These systems could automatically adjust operating parameters, speed profiles, power application rates, sanding strategies to optimize performance for the specific conditions ahead. Advanced wheel and rail materials are also under investigation. New steel alloys and surface treatments might increase the base friction coefficient or provide better performance under contaminated conditions. Ceramic composite materials show promise for even higher friction levels, though cost and durability remain concerns. What's clear is that, after 2 centuries of development, the steel wheel on steel rail remains an elegant, efficient system for land transportation. The apparent simplicity of smooth steel rolling on smooth steel belies an incredibly sophisticated interplay of materials science, mechanical engineering, and control systems, all working together to ensure those wheels keep gripping, no matter how extreme the pressure. The ability of locomotive wheels to maintain traction under extreme pressure is not magic. It's the result of understanding and applying fundamental physics principles through brilliant engineering. From the intentional weight of the locomotive maximizing normal force to the sophisticated electronic systems maintaining optimal creep levels, every aspect of the design works toward the same goal: converting rotational motion into forward progress as efficiently as possible. The next time you see a freight train hauling thousands of tons of cargo up a mountain grade or accelerating smoothly from a station, you'll know the incredible science and engineering that makes it possible. Those small contact patches, each no larger than a coin, represent one of humanity's most successful applications of friction physics, refined over generations into a system of remarkable capability and reliability.